Welcome. In this film, we'll explore methods for controlling injury hazards on the job. Illustrated transcripts are available on Kansas State University's Gen Ag 712 course website and through a link provided on our YouTube channel. Each year in the U.S., about 5,000 workers are killed and about 1 million suffer lost time injuries on the job. This film examines broad strategies for reducing exposures to hazards such as vehicles, machinery, tools, falls, violent assaults, electricity, and fires. A consensus standard known as ANSI Z10 serves as a guide for on-the-job injury prevention in the U.S. ANSI Z10 is published jointly by the American Industrial Hygiene Association and the American National Standards Institute. The ANSI standard includes a hierarchy of controls in which the first priority is to completely eliminate hazards or at least reduce the dangers by substituting safer materials, equipment, facilities, and processes. When hazards cannot be eliminated, the next priority is to protect workers with engineered devices such as guards and barriers. Supplemental controls include less effective methods such as warnings, administrative controls, and personal protective equipment. We'll begin our discussion of hazard control by examining the closely related methods of elimination and substitution. Some hazards can be eliminated or substantially reduced by switching to safer materials, equipment, facilities, and processes. As an example, let's consider belt-type man lifts, which can still be found in some manufacturing facilities, such as this flour mill. This man lift consists of a motorized belt with handholds and platforms for standing. To ride the man lift, a worker grabs a handhold, steps onto a platform, travels to another floor, and then steps off, all while the belt is moving at a constant speed. Many workers have been killed on man lifts, usually by falling through the open shafts. To eliminate the hazard, many employers have removed man lifts and switched to stairways as a safer method for traveling between floors. Elimination and substitution can also reduce hazards associated with chemicals that strip paint from wood. For instance, some paint strippers emit flammable vapors. We can eliminate the risk of fires and explosions by using substitute products that are non-flammable. As a final example of elimination and substitution, consider this electric drill. The drill is designed to be plugged into an outlet and held by the worker. This creates a risk of electrocution if the drill or its cord become damaged. The risk is much higher where workers lean or hold on to grounded surfaces such as soil, concrete, and water pipes. To reduce the risk of electrocution, we can substitute a cordless rechargeable drill such as this. When used according to the manufacturer's instructions, the drill's low-energy battery is unlikely to cause a serious electrical shock even when the worker is in full contact with grounded surfaces. When hazards cannot be eliminated, the ANSI standard recommends engineering to reduce the risk. Engineering controls are safety features that are built in or added to inherently hazardous equipment and environments. These controls may provide a high degree of protection, but only if they are used and maintained properly. To illustrate, this tractor supplies mechanical power to farm implements through a power takeoff or PTO, which is controlled by the operator. When engaged, the PTO stub rotates at high speed. With the PTO turned off and the tractor engine shut down, a driveline can be attached to the stub. During operation, the PTO is engaged to transfer rotation through the driveline to implements such as this mower. PTOs are useful, but they are also hazardous. In fact, many farmers have been killed by entanglement in rotating PTO stubs, drive lines, and U-joints. We still use PTOs because safer substitutes are often not feasible. However, modern tractors and implements are equipped with engineered shields to protect against the hazard. As a case in point, these heavy steel guards help workers avoid stepping or leaning on the PTO stub while it is rotating. Also, the mower's driveline has an outer shield that fully encloses the moving parts. If we could see inside the shield, we would observe the actual driveline that rotates inside. Chains keep the outer shield stationary even when the driveline is spinning. PTO shields are classified as engineering controls because they are built into equipment to protect workers from hazards that cannot be eliminated. Engineering controls also include safety features that protect workers from hazards on power saws. As examples, this saw has a rigid metal guard on top and a movable plastic guard on bottom to protect users from the blade. The bottom guard slides open during use, but just far enough to make the cut. The guards are engineering controls because they are built in to protect against a hazardous blade that cannot be eliminated. Since the saw uses electricity, other engineering controls are employed to protect workers from the hazard of electrocution. For instance, the saw is double insulated, meaning its exposed metal parts are separated from electricity either by an extra layer of insulation or by insulation that is specially reinforced. Electricity is still present, but double insulation reduces the risk. For added protection against electricity, we can plug the saw into an engineering control known as a ground fault circuit interrupter, or GFCI. The GFCI monitors electric current and immediately shuts off power if anomalies suggest that an electrical shock may be happening. The GFCI's quick action greatly reduces the extent of injury when shocks do occur. Some engineering controls are called interlocks. These devices prevent equipment from operating unless certain conditions of safety are met. For example, this industrial cutter has a sharp blade and powerful motor. It is designed to slice through reams of paper, and it can easily amputate hands, arms, and other body parts. The cutter has a system of interlocks to keep operators' hands out of the path of the moving blade. Specifically, the blade cannot be activated unless the operator depresses the foot pedal while simultaneously pressing two widely spaced hand-operated buttons. The interlock system is an engineering control because it is built into the machine to protect workers from a hazard that cannot be eliminated. Another type of interlock is the handle-mounted control bar found on modern walk-behind lawn mowers. When the mower is not in use, a spring keeps the bar in the up position. When the bar is up, interlocking controls stop the mower's blade from spinning. The blade operates only while the spring-loaded bar is held down. This type of interlock is sometimes called a presence-sensing device because it indicates whether a person is present at the controls. It is also called a dead man switch because the blade stops if the bar is released, as would happen if an operator died or became incapacitated. Interlocks are also present on modern skid steer loaders. Skid steer loaders get their name from the steering mechanism, which causes them to skid while turning. Many workers have been killed by sudden loader movements while reaching in to operate controls from outside the cab. Interlocks can prevent these injuries by disabling the controls unless an operator is in the seat. For instance, this loader will not operate unless the worker is seated with the lap bar pulled down. Some loaders have interlock switches in the seatbelt mechanism. This loader has an interlock that prevents operation unless the worker is buckled in with the front door closed. The common purpose of all these interlocks is to disable hazardous equipment until the operator is safely positioned. Besides creating safer machines, engineering controls can reduce hazards associated with buildings and other environments. The railing shown here is an engineering control that was attached to a building to reduce the risk of falls during a roofing project. Where livestock are handled, engineering controls may take the form of pens, alleys, chutes, and gates. These devices prevent injuries by separating workers from powerful animals. Some engineering controls are designed to relieve excess pressure from vessels such as water tanks and boilers. The relief valve shown here releases water in a controlled manner if temperature or pressure rise to dangerous levels inside the water heater. Without this device, the tank could explode or release scalding steam if the thermostat malfunctioned. As a final example of engineering controls, electrical fixtures in grain handling facilities and chemical plants are designed to keep electric sparks and heat from setting off large explosions. Some of these fixtures are made to contain heat and flames if a small explosion occurs within. Others prevent flammable materials from entering the fixture in the first place. Warnings are supplemental controls designed to capture attention and alert workers to immediate hazards that cannot be eliminated. For instance, engineered guards cannot fully eliminate the risk of injury from a lawnmower's spinning blade. Since some hazard remains, manufacturers attach warning labels to alert workers of the risk. Other examples of warnings include traffic signals and signs that draw our attention to roadway hazards. Similarly, backup alarms on vehicles warn bystanders to watch out for backing equipment. Smoke detectors likewise sound a warning in the event of a fire. As a final example, custodians use wet floor signs to warn building occupants that floors may be slippery after cleaning. Administrative controls are used in addition to warnings when hazards cannot be eliminated. Administrative controls include safe work procedures, housekeeping, protective scheduling, and training. To begin, let's consider safe work procedures. Although this saw includes blade guards and other engineering controls, workers can still get hurt if they do not work safely. For instance, the manufacturer of this saw recommends that workers protect their hands by keeping them at least 6.5 inches away from the blade whenever it is spinning. As another example of safe work procedures, forklift operators must keep loads low while driving to reduce the risk of tip-overs. Along with safe work procedures, housekeeping is also classified as an administrative control. We can employ housekeeping to reduce the risk of falls by immediately cleaning up slippery floor contaminants such as the wheat that was spilled in this milling facility. Another administrative control is scheduling to limit hazardous exposures. As a case in point, we can reduce opportunities for falls by scheduling routine mopping for times when the fewest people are in the building. Training is yet another administrative control. If hazards cannot be eliminated, we train workers so they can recognize risks and respond appropriately. The last category of controls in the ANSI hierarchy consists of personal protective equipment, or PPE. Personal protective equipment is specialized gear that workers wear to reduce exposure to hazards. PPE often fails, so it is considered a control method of last resort, appropriate only after elimination, substitution, and engineering controls have been employed to the greatest extent feasible. One example of PPE consists of specially designed safety glasses that help protect workers' eyes from wood chips thrown by power saws. Personal protective equipment also includes special earmuffs to protect hearing and a respirator to protect the airways from wood dust. Personal protective equipment also adds a measure of safety when using chainsaws. Safety glasses and earmuffs protect vision and hearing. A hard hat protects the head from falling limbs, and a face shield protects the face from flying debris. Finally, chainsaw-resistant chaps prevent the saw blade from cutting the legs. Workers also use personal protective equipment to prevent cuts and punctures in meat processing facilities. The glove shown here is made of cut-resistant engineered fibers to protect the left hand from accidental contact with the knife. A protective apron made of chain mesh is visible beneath the cloth apron. The chain mesh protects against cuts and stabs to the chest, abdomen, and upper thighs. As a final example of personal protective equipment, workers often wear body harnesses with lifelines to reduce injuries due to falls from roofs and other heights. Personal protective equipment comes in many other forms for a variety of jobs. However, since PPE is prone to failure, it should be used only as a supplement to more effective methods of control. The ANSI hierarchy is just one of many that have been proposed over the years. As another example, Roger Jensen has outlined an alternative hierarchy with strategies that tend to be more specific. Some of Jensen's controls are identical to those in the ANSI hierarchy. However, a few are quite different. Many other hierarchies exist, including those proposed by Ralph Barnett and Dennis Brickman, William Haddon Jr., the National Safety Council, and the Occupational Safety and Health Administration. In short, there are many well-reasoned approaches to hazard control, and safety professionals are encouraged to adopt methods that work best in each situation. Let's review what we've covered in this film. The ANSI standard recommends that we first attempt to eliminate hazards, or at least reduce them through substitution. When hazards remain, we reduce risks through engineering. Finally, we supplement these methods with less effective strategies such as warnings, administrative controls, and personal protective equipment. Elimination actually removes the source of injury. It is effective, but it works only if we can substitute less hazardous materials, machines, facilities, environments, or work procedures for those we eliminated. As an example, we can eliminate high-energy electric current if we replace this plugged-in electric drill with a cordless rechargeable model having a low-energy battery. Similarly, we can eliminate the risk of fires from paint strippers if we switch from flammable to non-flammable formulations. When elimination is not an option, we use engineering controls to make equipment and facilities as safe as feasible. Engineering controls do not eliminate hazards, so a degree of danger will still be present. Engineering controls can take many forms, including guards around moving parts and interlocking controls that keep operators out of harm's way. Engineering controls can also protect against electric shock. Examples include ground fault circuit interrupters and electrical insulation. Guardrails are engineering controls that are attached to facilities and equipment to protect workers from falls. Relief valves are engineered to protect against hazardous temperatures and pressures. Finally, explosion-proof fixtures are engineered to keep electrical sparks and heat from triggering large explosions where flammable dusts and vapors may be present. Warnings are controls that alert workers to immediate hazards that cannot be eliminated. Warnings are effective only to the extent that workers recognize, understand, and obey them. Warnings can take many forms, including traffic lights, backup alarms on vehicles, and signs or labels. Administrative controls can provide additional protection, but only to the extent that workers understand and comply. Administrative controls include safe work procedures, such as keeping hands away from moving machine parts. Another administrative control is housekeeping to reduce clutter and slippery contaminants. Other administrative controls include scheduling hazardous conditions for times when the fewest people will be affected, and training workers to do their jobs safely. Personal protective equipment, or PPE, consists of gear that workers wear to prevent hazardous exposures. PPE is effective only if it is selected and used properly. Personal protective equipment comes in many forms, such as safety glasses, helmets, face shields, hearing protectors, cut-resistant clothing, and personal fall arrest systems. This has been an overview of hazard control methods for occupational and agricultural injury prevention. No single control strategy is appropriate for every situation, so safety and health professionals are encouraged to consider a variety of methods, including those discussed in this film.